talk by Michael Kerber from Graz, and he'll talk on novel computational perspectives on consistence.
Yeah, thank you so for inviting me. So I already were here last week for the school, and I gave a talk on computational perspectives on persistence. So this is obviously a follow-up. And in this talk, last Friday, I introduced the basic steps that are needed to compute persistent homology on data sets. And there are three steps involved. So first, out of your raw data, or point cloud data, usually you compute some multi-scale representation of the shape. And we learned about WIPs and check complexes. Yeah, I guess most of you know about these constructions. Then you have to compute the barcode out of this. And I talked about matrix reduction on Friday, and we just heard about it again. And then finally, the last step is, out of your barcodes, you want to sort of improve your understanding of the data. And one way, or one necessary tool for that, is you have to be able to compare persistence diagrams. And I defined bottleneck distances last Friday. And well, today I want just to give, for every of these three steps, I want to give you a new development that has happened in the last 2 years. So it's a kind of an ambitious plan in 45 minutes, but let's see how far we get. So I go from left to right, so this is the outline. I start with getting a filtration out of a point cloud. And well, here's a quick recap on check filtration. So formally, you take your points, you take balls of radius alpha, and you take the nerve of these points as your simplicial complex. Then you get the check complex. And when the radius increases, you get larger and larger complexes, and then you get the so-called check filtration. That's important in TDA because it corresponds to the thickening of the balls. This is something that you often want to consider when you study the data set. There are also WIPs complexes that we have heard about. They're almost the same, and I will not go into much of the differences between them. Most what I say will hold for WIPs and for check complexes. And the problem with both is just the size. At least when you don't do thresholding, then you have, for computing the k-skeleton for n points, you have n to the k plus 1 many simplices. And that's way too much, even for moderate-sized data sets. Now, the idea is that maybe one way of speeding up is not to compute the exact diagram of the check or WIPs filtration, but only an approximation. And that means, well, formally you define approximation in terms of bottleneck distances, but just informally, from the diagram you want to compute, you compute some sort of approximation, so there should always be some feature close by. Yeah? And the hope is that you can find a filtration which has this guarantee and is much smaller than the check filtration. Yeah? And this has been studied, so the first work of this was by Don Shi 5 years ago. And the rough idea is that when you have 2 points which are close to each other and you are on a large scale, then these 2 points look like 1 point, and you can just contract these 2 points into one. And of course, you can also have a cluster of points close by. You just can represent the cluster as 1 point on a large scale, and in this way you avoid doing all the connections. So this is the sparse WIPs filtration, and of course there are a few details, when do you contract and all that, but the result is that with some approximation parameter epsilon, you get a 1 plus epsilon approximation of the WIPs filtration and of the WIPs diagram, and the number of simplices that you need is only linear in n. So it's n times 1 over epsilon to the O of delta k. Delta is the doubling dimension of the point set. And if you don't know what that is, you can just very roughly replace it by d, which is the ambient dimension of the point set. Often delta can be much smaller, but d is an upper bound. Okay, and that's very good because now if, let's say you have something like 10,000 points and k is equal to 4 or 5, then 10,000 to the 5 is too large, but 10,000 times this constant might still be doable. Yeah. And there's a lot of follow-up work that all these works roughly get the same guarantees. Some of them are for WIPs, some for check, and yeah, they roughly all get the same sort of result. Now, what I want to talk about is some different sort of approximation scheme. So this is joint work with my student Aruni Shudari and with Sharat Raghvendra. So our result is worse in 2 ways. So first, instead of 1 plus epsilon, we only have an order of d approximation. WIPS filtration, let's say. And also we have to replace the doubling dimension by the ambient dimension. That makes it again worse. And the only advantage that we have is we replace the k in the exponent by a log k. Yeah? So the way I explain it now, it doesn't sound too exciting, but the advantage is with this bound, you can now combine this with dimension reduction techniques. And the result we get is you have an arbitrary point set in an arbitrary dimension, like n points in up to n dimensions. You can always find a polylogarithmic approximation of your filtration, and the size is polynomial in n, and completely independent of d. Yeah? The constant here is something like 10. Yeah? Now, of course, in practice, n to the 10 is not too appealing, but at least from a theoretical point of view, it's interesting that you can kind of beat this exponential dependence on a dimension. We also have a lower bound, which I will not talk in detail today. So the result is if you want a very close approximation, so 1 plus delta, and delta is roughly smaller than 1 over log n, then you can prove that any approximation scheme that you may come up with has a super polynomial size in n. So you cannot hope that this result extends to all approximation factors. Yes, and I want to give you the idea of our construction. So first I show you what we don't do, but it is close enough to what we will do in the end. So what you could do is you have a point set, and now you just put a grid in your ambient space. And the grid cells that contain an input point we call full. So these are the colored pixels here. And then we can just take the nerve of these pixels as our approximation. Yeah? So this blue structure here would be now our approximation of the check complex. So how well is that? Well, this is quite an easy exercise. The diameter of a cell is alpha times root d in d dimensions. So that's the length of the diagonal. And if you have two cells which are not neighbors, they must be at least alpha apart from each other. It's also easy to see. And with these two ingredients, then it is fairly simple to show that this construction gives you a root d approximation of the check complex. And that's better than what I promised on the previous slide, right? On the previous slide I said order of d, and this is root d. The disadvantage of this construction is that you have a highly degenerate setup because every vertex of the grid is adjacent to 2 to the d pixels, and if they're all full, then you have to take all k subsets of these 2 to the d many sets. And then you end up with the same size, roughly, than what in Xi's bound was given. So we made things only worse. We have a worse approximation and the same size. But, well, nobody forces us to use the integer grid. We can also just use another grid, and for instance, the hexagonal grid in the plane, then we don't have a degenerate setup. And we can do the same thing, right? We take the full hexagons and we take the nerve of the hexagons as our approximation. That's nice, but how does this work in high dimensions? Yeah? And the construction is the permutahedron. Well, this is the Werner region of a lattice. It's called the A-star lattice. And the definition is just this. So you take the point 1, 2, 3 up to d plus 1. You take all permutations of its entries, then you get d plus 1 factorially many points, and you take the convex hull of all of these points. That's the permutahedron. Now this lives in d plus 1 dimensions, but of course all these points are on a common hyperplane because the sum of the coordinates is the same. So you can just look at this polytope in this hyperplane, and then you get a picture like this. So this is the permutahedron in 3 dimensions. Now you can already see there's a lot of symmetries and a lot of beautiful combinatorial properties which we make use to some extent in the paper, but I just talk about the major things here. So compared to the integer grid, the diameter of a permutahedron is still root d, like for cubes. And if you have 2 permutahedra in this tiling, I mean obviously they tile the space, yeah, because it comes from a lattice. If you have 2 permutahedra in a tiling and they are not neighbors, then they are roughly alpha divided by d apart from each other. For cubes we had alpha, here we have alpha over d, and this over d is the reason that we get only a d approximation. Yeah? Okay, so now our approximation scheme is really that we tile the d-dimensional space with permutahedra, we define full permutahedra to contain an input point, and we take the nerve of these permutahedra as approximation. And this, yeah? Well, you can define a lattice. I mean, you can define d vector, independent vectors, and you take all integer combinations of them. And then when you have a point and you take its Voronoi region, it happens to be this permutahedron. So the size of the, well, to get the size of this approximation, you only have, basically you have to count the number of k faces in the permutahedron. And this is a standard thing, and you can prove that the number of k faces is at most 2 to the d log k. And so the size of one star, of one vertex, is at most this number, and you multiply by n, and you get the size of the approximation, an upper bound for it. Okay, now how do we prove interleaving with the WIPS complex? So we use pretty much a standard approach. So far I only explained to you how we define this x on every scale. Now, of course, we have to connect the scales, and we have also to interleave it with the WIPS. And the interleaving maps, they are easy to define. So for interleaving, this is a simplicial map, so we have to say what we do with vertices. So every vertex of the input, we just map to the closest permutahedral center, and every permutahedral center we map back to the closest input point. These are the maps phi and psi, and we just define theta to be the composition of the two. Yeah? And then we get, of course, this triangle commutes for free, and you can easily prove that G is the inclusion, so this triangle also commutes. Yeah? It's a simple lemma. And then, in this way, you can prove the interleaving with the WIPS. I'm just saying that because in 2 slides I will present an alternative. Okay, now I talked about dimension reduction, and at this point, when I gave this talk before, I usually had complicated formulas and people got very confused, so I just took a picture. Yeah. So what is the idea? So you have a high dimensional point set. So again, I want you to think of d, the dimension now, to be in the order of n. Yeah. And the dimensional reduction results, there is the Johnson-Lindenstrauss lemma and similar results. It says you can take your high dimensional space and you can project it to much lower dimensional space, something in the order of log n. So you go from n dimensions to log n dimensions. And you do just a random projection to a random hyperplane or a random subspace in dimension log n. And you will, with high probability, you will approximately preserve all pairwise distances of the points. That means from a kind of WIPS point of view, this point set and the projected point set are almost the same. And then you can, in the lower dimensional space, you can use our permutahedral approach, get a filtration, and compute its barcode or persistence diagram. Yeah? And the distortion is then, you have a logarithmic distortion in the first step and a logarithmic distortion in the second step, because the space is now logarithmic. Now, already this morning was mentioned, maybe you say, my data is not Euclidean, but I have some arbitrary discrete metric space, then you can still use that. There is the embedding result by Bourgain, which says any finite metric space can be embedded in Euclidean space in dimension log squared. So you first do that. That gives you another logarithmic distortion. Then you project dimensions, and then you use permutahedral approximation. And if you do this whole pipeline, you get log cubed n as a distortion parameter. And when you do the calculations, then you see indeed the size of the filtration does not depend on the dimension that you started with. Yeah. So that's the dimension reduction. Now I want to talk about something that we submitted 2 weeks ago. So this is an extension of this result. So it's a different approximation scheme. So in this case, we really take the integer quid, and now we take the vertices of the quid, not the pixels, but the vertices that are kind of close by the input points. Yeah? So we have a collection of quid points, and on this we define some sort of approximation scheme. And it's a bit technical. The idea is that you take a subset of the barycentric subdivision of the cubical quid. Yeah? And you have just to, in a smart way, select the right simplices such that the size doesn't become too large. But when you do that, you get basically the same guarantees as before, but instead of a d approximation, you have a fourth root of d approximation. So that's quite a bit better. And this result, I think, is interesting for 2 more technical reasons. So the first thing is, remember the interleaving picture from before. So usually when you want to prove your approximation is close to WIPs, let's say, you have to find simplicial maps connecting them. And what we did here is we had quite some problems to find these connecting maps on a simplicial level. And what we do instead here is we define acyclic carriers from one complex to the other and vice versa. And then we use the acyclic carrier theorem, which tells us when you have an acyclic carrier, there is always a chain map connecting the two chain complexes. And then we can actually prove the interleaving without ever explicitly constructing the interleaving maps. We just exploit the existence of them. Yeah? And I think that's quite nice, and it can be convenient for such approximation schemes because you never need to know the interleaving maps explicitly. It's enough to know that they exist. For computations, they are not needed. And the second step is a very simple trick, and it's not the main point of the paper, but I still want to explain this here. So after you did this interleaving business, you have, in this particular case, you have a map that goes from the approximation at scale alpha to the approximation at alpha times gamma. And in this particular example, the backward interleaving map goes on the same scale, so it does not shift. Yeah, so it's asymmetric. And then you can just redefine your approximation scheme A by just multiplying every scale by root of gamma. So you kind of make it symmetric. And in this way now you have made a gamma interleaving, you have turned it into a root of gamma interleaving, just by renaming the complex. Yeah? And in this way we get from a square root of the approximation that we originally get to a fourth root of the. Yeah? It's actually a quite simple trick when you see that, but it really helps here in improving the guarantees. Okay, so this was number one. Now we have some sort of multi-scale filtration, and the next step is we compute persistence. And this is exactly the topic of this morning's talk. So here's a recap of this. So usually you have a filtration, a nested sequence of simplicial complexes. You can put this whole data in a boundary matrix and you reduce, or maybe you don't put it in a boundary matrix, but only implicitly, and you compute the barcode. And there is a lot of efficient software for this. So what I want to talk about is not yet another approach for that, but I want to talk about a slightly more generalized setup. So this is the simplicial towers. And the idea is that now we don't have a nested sequence, but we are also allowed to contract vertices. Yeah? Like here, from the first to the second, you have a few simplices added. Now you decide for some reason you want to contract these vertices into one, and then you keep including, and so you interleave between inclusions and contractions. And and you can phrase this algebraically as a sequence of simplicial complexes and arbitrary simplicial maps acting between them. And from an algebraic point of view, there is no problem. You still have the barcode because functoriality of homology still works. Now, why is that important? Well, in the first part of the talk, I was not very precise, and I called everything a filtration. But in fact, when you do these approximation schemes, you don't have a filtration. The simplices are not included in each other, but you have precisely this problem. Sometimes you want to get rid of vertices. Yeah? So that's why this problem became relevant in the last years. And the problem is now having such a tower, we call this a tower, get the barcode of the tower. And has this been done before? Yes. There was work by Tamal and others. And when you look in the paper, then in an early section, they describe the coning idea. And it's not exactly, I describe it in a slightly different way, but the idea is the same. So the idea is that you have a tower, so here we contract u and v, and then we contract x and y. So this would be a simple example. And we want to find a filtration now that has the same barcode. So we only include stuff and we get the same result. And the idea is very simple. So when you contract u and v, let's say we contract u into v, so we get rid of u, then the rule is every simplex that is attached to u should also be attached to v. So in this case, for instance, x is attached to u, so in a coning we have to attach x to v. But then we create, of course, a cycle, so we also have to attach x to the edge uv. Yeah, so this is the second rule here. And in this way, we get an inclusion, and we do the same in every step. So here, for instance, when you do this example, this complex already has the tetrahedron u, v, x, y included by the coning rule. And why do they have the same barcode? This is quite easy to see. You always can define a sequence of elementary collapses from the lower to the upper complex. And in this way, you preserve even the homotopy type. And then you can show that also the barcode. So this is compatible with the maps. Good. So this is coning. Now, in this paper, Tamal and his co-authors do not use this. They just describe this, but in their algorithm, they don't use the coning. Instead, they define the annotation algorithm, which is a variant of the cohomology algorithm, and they show that this algorithm can handle the contractions directly. So they don't have to convert to an filtration. Yeah? And why does this seem to be a good idea? Well, you can see in this example that this coning filtration seems to be very large. You include more and more simplices, and it seems to be very inefficient to do that. And the question that we ask is whether this is really true. Yeah? So how many simplices do we really get from coning? And the answer is, when you think about it a few minutes, you will see, yes, it can be very bad. But now I want to show you two simple heuristics, and these two heuristics make coning competitive. So here's the first thing. So we call it active coning. The idea is that every vertex in the tower, or also in the filtration actually, every vertex in the filtration is either active or inactive, and inactive means that it has been contracted away in the tower. So here U becomes inactive, and the next step Y becomes inactive. And we call a simplex inactive if it has one vertex that is inactive. Yeah? And the coning rule is now, once we do the same as before, so when U and V are contracted, we copy everything attached to U, also to V, but we do this only for the active simplices. So if a simplex becomes inactive, we never look at it anymore. It is still there, but we don't copy it around. Yeah? So that's step number one. And you can, again, this argument with the collapses still works, so you don't lose anything. And this example is a bit bad because the picture looks the same, but you can observe here that the tetrahedron UVXY is not there. The reason is that you would not copy the triangle UYV to X, just because this vertex is inactive. Yeah? So you save a few simplices in this example. Second heuristic. So whenever we have a contraction of U and V, we have actually a choice to make. Namely, we can either get rid of U or we can get rid of V. Yeah? It's symmetric. It's just up to renaming, it's the same thing. Now the question is, what should we do? And when you look at these pictures and you look at the title of this slide, you might guess the idea. You just take the complex that gives you a lower number of simplices. So in this case here, this has only 3 triangles, this has 5, so we probably go for the left one. Yeah? I think if you had to implement this, you would do this anyway without much thinking about it. Yeah? Okay, so this is greedy coning, and of course you can combine this with the active idea. And the theorem, and this is joint work with my student Hannah Schreiber, the theorem is that now having any tower, and this tower has in total n inclusions, so the size is n, you can always find an equivalent filtration, and the size of this filtration is only delta times n times log n0, where delta is the dimension of the tower, so the highest dimension of a simplex, and n0 is the number of vertices. So in realistic examples, the number of vertices is much, much smaller than the number of simplices, so log n0 is really a small number. And as long as your complex is not too high dimensional, this is only really marginally larger than the tower. And the advantage should be clear. Now you have a filtration, and now you can use any software that you want. You can use FAT or Irene or RIPSA or whatever is more efficient next week. Yeah? So, okay. I want to go into the proof of this also to some extent. So the main tool to prove this conversion result is the contracting forest. The contracting forest has leaves, and these leaves correspond to the vertices of the tower. And you have an inner node whenever you have a contraction of the 2 corresponding vertices. So this would be the contraction forest of this example. But of course, you can contract. You can again, there can be trees formed by contracting more. Now I assign a cost to every interior node, and the cost is just how many simplices I add caused by this contraction. And then I claim it is enough just to bound the cost of all interior nodes. Because when you go back, you have n simplex additions. Of course, these n simplex additions in the tower will also happen in this inclusion. So the size here is n plus the cost you have for every contraction. Yeah? And this n you can just ignore. So we bound the cost of the contractions. And for that, we need another definition, which is called the E set. So we take an inner node of our contracting forest, and it has a subtree, and it has leaves in the subtree, and they correspond to vertices in the tower. And we take all simplices which are incident to at least one of these vertices. And we call this the E set. You can also say it's the union of the stars of these vertices. Yeah? Okay, that's the definition. And now we have a simple lemma which says if we have an independent set of nodes, and independent means none of them is an ancestor of the other, then we can bound the sum of the E sets in this independent set just by delta plus 1 times n. And this is very easy to prove because every simplex has at most delta plus 1 many vertices, so every vertex can only appear in delta plus 1 of these E sets, and you have n simplices. Okay, now the question is what is the relation of E sets and the cost of the contraction? And this is the main lemma in this whole argument. So now you look at an upward path in your contracting forest, like this one. So you have 4 queen nodes here. And the lemma is that you can bound the total cost of all these queen nodes together by the size of the E set of the highest node. Yeah? And this is the step where the greedy coning is important. Without greedy coning, this would just not be true. And now you can take an independent set of upward paths. That just means that the top vertices are independent. So these 3 colored paths here are independent. And the size, now you bound the total cost of all these nodes together. This is bounded by delta times n, just by combining this lemma with the lemma from the previous slide. Okay, so we have bounded the cost of all these colored nodes now. And now the idea is that you can decompose your forest into a collection of at most log n0 many such collections of independent upward paths. So basically you can define an algorithm that decomposes, you first define this, you take these upward paths, you pay delta n for them, you remove them, then you find another collection of upward paths, pay another delta n, remove them, and after log n0 many steps you have paid for everything. Yeah? And this is how the result follows. Good, so this was the main theorem in the paper. Now there is a lot of implementation work, which unfortunately I can only go into a little bit detail. So of course you can implement this. I showed you the implementation. You just have to define these implement these 2 heuristics. And we can do this in a very memory efficient way, in fact, in sort of a streaming algorithm. So the amount of things we have to keep in memory is very small in this conversion. And we implemented this, and it turns out the size of the filtration that we get is really only a bit larger than for the tower, much better than the theory predicts. In most realistic examples, it was less than a factor of 2 that our filtration is larger than the tower. Yeah. And you can even go one step further. That's the second part of the paper. If you compute persistence on this converted sequence, you can actually also make this more space efficient. And the idea is, roughly speaking, remember that we had inactive simplices in the process. And remember, in the boundary matrix, every column corresponds to a simplex. The idea is now, when a simplex is inactive, you can remove the corresponding column from the boundary matrix because you will not need it anymore later. Actually, the way I said it is wrong. You have to be a bit more careful, but it's almost correct. Yeah? So with a little bit of more reasoning, you can show that there is a space-efficient algorithm for persistence in these cases. And these days, it is fashionable to say we can compute huge data with little memory. So here's our contribution. We have a tower with 4.6 billion inclusions, and we only need 68 megabyte of memory here. And we have, the reason is that this tower is very long, so you have a lot of things happening, but every single complex in the tower is very small. And the memory consumption depends only on the size of the intermediate complexes, not on the length of the tower. And we have the Sophia library where you can try this out if you want. How much time do I have left? 20 minutes, perfect. Okay. Good. So this was step number 2. Now we have our barcodes, or now I assume we have persistence diagrams, and we want to compare them. Here's a slide that I had up last Friday already. So imagine you have n persistence diagrams, and they correspond to n shapes. And now maybe you want to classify your shapes according to the diagrams. And then what you could do is you just compute all pairwise distances, and then you cluster them, maybe. Yeah? The problem is when you do that, then you have a quadratic number of distance computations, and this can be more expensive than computing the diagrams themselves. So we need an efficient way of computing the distance between two diagrams. Now, how is the distance defined? Well, the idea is you have two diagrams and you want to pair them in a one-to-one fashion. You have to pair every point of every diagram, but you have the special rule that if you want, you can always pair a point to the diagonal. And then you define the cost of a pair, which is just the distance with respect to some LP metric. And now you have a choice. You can either try to, among all possible pairings, you try to minimize the longest edge in the pairing, then you get the bottleneck distance, or you minimize the sum of the costs, and then you get the Wasserstein distance. And for both of them, there are stability results proven, and there are many other distances. I guess we might even see some of them in this workshop, but I focus entirely on these two classical distances. Now, how do we do this computationally? There is this trick that I also explained on Friday. You can turn this into a graph problem by just saying the projection of every red point becomes a point in the blue diagram and vice versa. And then you have the same number of red and blue points. Now you can set up a complete weighted bipartite graph. And the weight of every edge is the distance between the points, with the one exception that points on a diagonal have distance 0. So you can always, if you want, map them for free. Yeah? So this is a perfectly well-defined graph, and now the question boils down to find a perfect matching in this graph with either you minimize the longest edge in the matching or you minimize the sum of the costs. Yeah? And this is well studied. For the first version, you usually use Hopcroft-Karp algorithm. For the second version, Hungarian. Yeah? So this is where the story could end, and we could have lunch, but no. So the thing is, we are not done. We have not exploited the whole structure of the problem. The reason is that this is not an arbitrary weighted graph, but the weights come from a distance. So this is a metric graph, but rather it is an almost metric graph because you have this diagonal special case. Yeah? But let's forget the almost for a minute and look at metric graphs. Can we do better for metric graphs, for bottleneck and Wasserstein matchings? The answer is yes, and this is known for a long time. You see, for instance, this paper, the title already tells you, yeah, geometry is helpful. So for metric graph, you can asymptotically improve the general graph algorithm. And the same is true for optimal assignment or for Wasserstein matchings. And I just cited the first work of this kind, but there is a long sequence of work that goes until today. So this is a very active field of research. Now, okay, so for metric graphs, it's fine. Now, does this diagonal business screw up anything? The answer is no. It's very easy to extend this to persistence diagrams, and I'm not sure of the real reference for this, but at least in the bibliographic notes of the Edelspooner-Hara book, you can read that this is possible. Yeah? So, short answer, geometry helps in theory. And what we did, it's joint work with Dmitry Morozov and my student Arno Nikmitov, we just said, well, it also helps in practice. And what we did is just we implemented a non-geometric and a geometric version of these bottleneck and Wasserstein matching algorithms for the plane. And we showed geometry is better. And for me, this was quite surprising that despite these works are 15 years old, nobody has ever tried to implement these theoretical approaches. Maybe because nobody had an application for that. But we have an application because persistence diagrams are something we really want to compute the distance of. And we compared it with Dionysus, which was, at least at the time where we worked on it, the only available software to compute these distances. And we outperform it on all examples we tried by a factor, by several orders of magnitude. So we'll see a plot later. And you can download this in our code from the Hera library. Okay, I will skip over bottleneck and I just talk about Wasserstein today. So the Wasserstein, just to remind you, we want to find the matching with the minimal sum of the costs. This picture is just to convince you that the best Wasserstein matching is not always the best bottleneck matching. Yeah? So they can be different. This problem is known under many names: assignment problem, discrete optimal transport, discrete Earth movers distance, and as I said, the Hungarian algorithm is the standard approach that is usually taught in classes. There are whole books written about that. I highly recommend this book, which presents 10 different ways of computing such a problem for general graphs. And one version from the book is the auction algorithm by Bertsekas, and that's the one that we use in our code, and I want to present this algorithm first. So before I start, the auction algorithm is phrased to not to minimize the sum of the costs, but to maximize the sum of the costs. But this doesn't matter because you can just negate every entry and then you turn maximization to minimization. Okay, but just have in mind we maximize now. We have n bidders and we have n objects. And now in the algorithm we maintain a partial matching. Initially this is empty and it gets larger, and we return, as soon as the matching is perfect, we return it. Okay? Every object has a price which is initially 0, and it increases during the algorithm. Also, every bidder has a certain appreciation for every object, which is individual. This bidder likes object 2 a lot, whereas this bidder has very different preferences. Yeah? So this is the setup. Now what do? We just repeat the following steps. We pick an currently unassigned bidder, and we compute the value of every object. That's just the appreciation minus the price. Yeah? So this would be the values of these objects. Now we pick the best and the second best valued object. And now we update the matching, so we just assign to this bidder the object that she likes most at this point. So we would just assign this bidder to this object. This of course makes this bidder unhappy. This bidder becomes unassigned and we have to reassign the bidder later. Okay, so this is how we update the matching. Now we have to increase the price, and we increase the price of the assigned object just by the difference between best value and second best value. That would be 2 here, plus some constant epsilon. Okay, and epsilon is something you choose, yeah? So we would have 10.1 or something, yeah? And this ends the description of the algorithm. Now we pick the next unassigned bidder and we repeat the same steps, and we do this until we have a perfect matching. Now you might wonder why epsilon. The reason is, if you put epsilon to 0, you can have the situation that you have a group of bidders which keeps stealing the same objects from each other without ever increasing the price. So you would run into a deadlock. And to avoid this, you need this constant epsilon. Now, why is the auction nice for our purposes? Well, for the following theorem. Well, let's call opt the maximal possible cost of any matching. So this is what we want to compute, and D is what comes out of the auction. So this is the cost of the returned matching. Then, of course, this matching is at most as large as the optimal one, but it's not much smaller. It's opt minus n times epsilon, where n is the number of bidders. And now you have a trade-off. When you put epsilon to be a large value, then this converges fast, but the approximation is rough. And for a small epsilon, it just takes longer. Yeah? There is some sort of optimization which we use. This is called epsilon scaling. The idea is that you do not just run the auction once, but you run it several times for decreasing values of epsilon. So you start with something very rough, you get some assignment, and now you set epsilon to be epsilon over 4, and you rerun the auction, and you use partial information from the previous one. Actually, you keep the prices And you have, of course, to prove that this works. But it works pretty well, and then you just run the auction for smaller and smaller epsilons and get better and better approximations. And what we do in the software is just we have some quality threshold that we want to guarantee, like we want a 1% approximation of the Wasserstein distance, and we just decrease epsilon until we can guarantee that this interval here is small enough. And this is what we return. You could also be more ambitious and say, well, you just decrease epsilon to be so small that you can guarantee that you computed the exact result. But then the auction becomes very, very slow. And when you look in this book that I showed you before, the auction is the slowest algorithm in the book. And the reason is that they always run the auction until exactness is guaranteed. But for approximations, the auction is actually very, very suitable. And I just want to remark that this is something that the auction is an important property of the auction. You can stop somewhere in the middle and you still get some reasonable bound for your result. When you take the Hungarian algorithm, you have no choice. You have to run to the bitter end, right? When you stop it in the middle, you have nothing meaningful. Yeah? So this is why the auction seems to be more suitable here. Now, I did not talk about geometry at all so far, right? Everything I said applies to general graphs. So how does geometry help here? So when we look at the geometric picture, of course, the appreciation is just minus the distance to the object, and the minus because of the maximizing, minimizing issue. And the crucial thing we have to do in the auction is we have to find the best valued object and the second best valued object for a bidder. And this you can phrase as a weighted nearest neighbor query. Remember, these objects are weighted by the price, and we want to find the best and the second best, which is determined by the distance and the price. And we use a very straightforward engineering approach using KD trees, where in every KD tree node we store the minimal price. I guess if you know KD trees, you already know what's happening here. If not, I want to show you a simple analogy. So imagine you have a bidder, and you are the bidder, and you live here, and you want to buy a certain item. Yeah, and you have shops in your city. And you already know in these shops, which are fairly close by, the item is not too expensive. So the value is pretty good. And now imagine your city is large, and there is some sort of quarter way outside, but there are many shops. Yeah, it's like a mall. The trivial solution is that you would have to check every of these shops here separately and check whether the value is better. But with this KD tree approach, we know, well, in every shop in this mall, we pay at least W for the item, and we have to drive a long way to get there. So we already know that these two shops are pretty good, so we don't have to check every single shop here explicitly, but we can just avoid checking all of them separately. So this is the rough idea of what is happening here. Yeah? And there is, of course, if you wonder, there is no formal guarantees. Asymptotically, we don't improve anything. But in practice, it works pretty well. Here's the plot. The red curve is the geometric approach that I just explained. And the blue curve is the non-geometric approach where we just go over every object separately and check. And well, performance-wise, in time performance, the difference is not so large. But in fact, we had to tune the non-geometric version quite a bit. And in particular, we use a quadratic amount of memory, even to achieve this time complexity. Otherwise, the non-geometric version would be much worse. Yeah? So in time, it's not so great, but in space complexity, the geometric version is much better. So message 1, geometry helps here. Message 2, when you compare to Dionysus, you see, well, you should observe this is a logarithmic scale here. So already for 1,500 points, which is not too much, we are better by a factor of 10,000. Yeah. Strictly speaking, we are not better because Dionysus computes the exact Wasserstein distance, and we, in this plot, only take a 1% approximation. So for some reason, if you want the exact approach, you have to stick with Dionysus, but if you are happy with an approximation, then there is little reason not to use our library, which is freely available. Yeah, so it contains many other, like it has a lot of parameters. Of course, this approximation factor is a parameter. You can also change the inner metric, and you can compute Q Wasserstein metrics for any integer Q. And I'm quite happy to see that many people also in this room have used this already. So you should, if you download it And if you see any bugs, there are probably still bugs in there. My student Arno usually fixes them within hours. Yeah, so we are very happy about feedback. Okay, and that's it. So I told you about one result for each of these steps in the pipeline. I again give credit to my students. So Aruni was working on the filtration part, Hanna on the simplicial towers, and Arno on the bottleneck and Wasserstein distances. And with that, I will stop and thank you.
Questions? So if I have some space with non-trivial homological features, sprinkle points randomly on it, and then compute Wasserstein distances between the resulting persistency diagrams, what will I get?
Oh, you mean if you take a diagram and then you put noise to the
will be kind of sharply peaked and stuff like that.
So you put noise to the diagram, yeah.
Between the persistency diagrams obtained by random sprinkling on the fixed space.
So we tried, the data that we tried was partially, it came from real data, but also we randomly generated. But usually the most examples we did it, we tried to simulate something that looks like a persistence diagram. Normally persistence diagrams have this shape. I think we also tried totally random, and it also seems to work. I mean, geometry seems always to help. So we don't know any example where the geometry would make things worse. Should it?
I was wondering for what P does it compute P Wasserstein distance?
For all integer p's.
All integer P's.
Yeah. It's the same. It's
I
the
assume
same.
it would be similar, but the code may not have been done.
No, but it does. Yeah.
So you mentioned that for the approximation there is no time bound. Did you say that, or something like no analysis for your auction algorithm?
Oh, the auction itself, there is an analysis. Yeah.
But what I know is that for bipartite graph matching weighted, if you do bottlenecking, like
Yeah.
the sum, you can approximate in linear time.
Yeah. So this is right. So for bottleneck, okay, we have bottleneck and Wasserstein. We have completely different approaches for both. For bottleneck, we actually use what this paper by Efrat et al. is suggesting. It's not linear. It is, isn't it? N 1.5, right? Log n. I think this is the complexity for the bottleneck. You say there is something better than this?
For approximation, not exact.
Uh-huh. Oh, okay, I didn't.
The Fox paper, I think, Duan and Betty,
Uh-huh.
1 plus epsilon optimal in linear time. And it's not that difficult.
Uh-huh. From this year or?
No, it's 2014.
Okay. Oh, okay. Thanks for letting me know. Yeah. But maybe this is so. This is the running time for the geometric version, and this is also what we implement has this guarantee, and the general one has something like this. So there is a whole factor of n. And I didn't show the plots now, but in the bottleneck case, actually we also implemented geometric and non-geometric, and we did some regression to test how well it is in practice, and it follows. Our geometric version follows very nicely this curve, and the non-geometric follows also this curve. So these complexities seem to be like the real thing, not unlike in the matrix multiplication case for persistence, where you have cubic in the worst case, but usually you don't see this cubic behavior. Here it seems to follow more closely the theoretic prediction. Is that you refer to the first part?
you tried to look at the distribution of fractal distribution of points?
No, I cannot. Maybe we talk offline. I don't.
This concept of self-similarity that arises when you discuss grading.
Yeah. I know there is a work. Yes, I cannot. But yeah, I'm not sure. I don't have anything good to say about it. Maybe we talk offline, then I can understand better what you mean. Okay.
Can you use this software to, if you have a bunch of, let's say, persistent diagrams, I'd like to find, another persistent diagram, maybe perfectly equally distanced from all of those. So I would have to have up to epsilon mean from these.
So that's a good question. The answer is no. The software cannot. You can use the software to verify whatever you found, but yeah, this is. I mean, it's not clear that this exists. First of all, and
So that's why up to epsilon probably doesn't. But up to epsilon.
in general, it will not exist. But if maybe you have a situation where you know it exists and you want to find it, I'm not sure. Maybe for bottleneck it's easier because you just have to look at. No, I would have to think about it. Yeah. Mm-hmm.
So the most computationally heavy version of this that I'm familiar with is we want a distance matrix between like a time series of persistence diagrams. So we have n choose 2 times that we want to do this calculation. Do you think there's any, in my understanding of your implementation, you would do each of these independently.
Mm-hmm.
Do you think anything might be gained by knowing about some of these previous calculations?
Yeah, if they are, so you mean these measurements are connected in some way that you know and you want to exploit.
So like Konstantin Leshchenko, for example, uses clusters to do these calculations with very long running times. And in some of these time series computations, there might be time steps in which the persistence diagram changes with very little.
Mm-hmm.
And then the dynamics changes and things change by a lot. So it might be that you've pre-computed certain matchings to be very close together.
Yeah.
And later on you could maybe take advantage of this.
Well, you could imagine some pre-processing, right? So I mean, if you find out that 2 diagrams are very close to each other, probably you can just say, well, then one of them I mean, it's like constructing a spanner in this graph, right? In this graph of persistence diagrams. But I mean, you want to do this avoiding computing all edges, yeah? I mean,
Earlier, how when you did your approximation, you used, you take a big epsilon, find something, and then go down to the next epsilon
yeah.
size. Is it possible when you have this time series thing to do the same thing, where you use the matching from the previous time step as like your large epsilon approximation?
No, but when you have a large epsilon, then you have, I mean, the distance, even if the real distances are very close to each other, the approximation might give you a distance which is far off, so it could still be big then. Or maybe not if you know that they are, yeah, I would have to think of it. It's a good question. So you want to exploit that there is some sort of, there is some relation between them, yeah. I mean, of course, in metric, when you construct spanners for points in Euclidean space, there is a lot of work that you avoid computing all the n squared many distances. But here, this is of course not very close to Euclidean space that we work with. I'm not sure how much of this work extends here. It's a good question here.
Okay, there's no further questions, so let's thank Michael again.